Lesson 54, polar coordinates and similar triangles. We're going to spend the majority of this lesson talking about polar coordinates. There are two ways to describe the location of a point on a coordinate plane in respect to the origin. One of those ways is by using rectangular coordinates, and one is using a polar coordinate. Today we're going to work on converting from polar coordinates to rectangular coordinates, but before we do that, we need to talk about the two different ways to describe this location of the points. The first one is using rectangular coordinates. A rectangular coordinate uses two numbers. The first number tells us the distance of the point to the left or to the right of the origin. This would be like our x-axis, but we don't call it, these are not x and y values. But one tells the distance of the point to the left or right of the origin. And one tells the distance of the point above or below the origin. All right, so in rectangular coordinates, we have two numbers. One tells the distance of the point to the left or to the right of the origin. The other tells the distance of the point above or below the origin. These two numbers are written as an ordered pair. And instead of using an x, y value, we're going to use the letters R and U. So it's an R, U value. All right, we're going to talk about what this means here in just a minute, but let's look at what polar coordinates are first. Let me shrink this up a little bit. All right, so that's rectangular coordinates. Let's talk about polar coordinates. All right, polar coordinates uses a distance and an angle to locate the point. Okay, so it uses a distance and angle. All right, let's talk about the angle first. In polar coordinates, positive angles are measured counterclockwise from the positive x-axis. Okay? Positive angles are measured counterclockwise from the positive x-axis. Then likewise, negative angles are measured clockwise from the positive x-axis. Okay, so positive angles are measured counterclockwise from the positive x-axis. Negative angles are measured clockwise from the positive x-axis. For example, on a coordinate plane, if I was finding an angle that was, let's say, 113 degrees. My coordinate plane is divided into perpendicular, two perpendicular lines with four 90-degree angles. Positive angles are measured counterclockwise, so they're going to be going this direction from my positive x-axis. All right, so here's the positive x-axis. If I go counterclockwise 113 degrees, well, from this axis to this axis is 90. Keep going a little ways further, and about right there is 113 degrees. So we're looking at this angle here, okay? What we're going to be dealing with primarily is going to be positive angles. We'll get to negative angles just a little while later. All right, so that is about the angle. Let's talk about the distance. Okay, the distance is a directed distance. It's as a vector. Okay, it's a vector from the origin. This vector has both magnitude and direction. Okay. Now, there are four different ways to name a polar coordinate. We can have a positive vector and a positive angle. We can have a positive vector and a negative angle. We can have a negative vector and a positive angle, or a negative vector and a negative angle. The way that we are going to name these, primarily for right now, is going to be with a positive vector and a positive angle. All right, so now what we're going to work on, now that we've discussed what rectangular coordinates and polar coordinates are, we're going to do some examples and I'm going to give you some steps, and then we're going to work through some examples in converting from polar coordinates to rectangular coordinates. All right, so let's look at some steps to converting from polar to rectangular. And as we do these steps, we're also going to work our way through an example. All right, so just to give you an idea, a polar coordinate looks like this. This is read a vector with a length of 4 and a positive 57-degree angle, okay? This degree, and then we've got the angle symbol here. All right, so we are going to convert this polar coordinate to a rectangular coordinate using these steps. All right, the first step is to draw a diagram and label the right triangle. All right, we're going to make a right triangle, and you're going to see what this looks like in just a second. Now remember, polar coordinates and rectangular coordinates are naming a location on a coordinate plane. So if we're going to draw the diagram is going to look like a coordinate plane with an XY axis. All right, we're going to draw the diagram based on the angle first. Now back in the previous slide, we know that positive angles, which is what we have here, are measured counterclockwise from the positive x-axis. All right, so here is the positive x-axis. We're going to be going counterclockwise. Also recall that from the positive x to the positive y is a 90-degree angle. Since 57 is less than 90, I'm going to estimate where 57 is, and I'm going to say it's about right there. We'll call that a 57-degree angle. All right, so right there is my angle. Now what I'm going to do is draw my vector. Vector always comes from the origin, and it's going to come out at that 57-degree angle. So here is my vector with a length of 4. All right, so we've got our 57-degree angle, and we've got our vector with a length of 4. Now notice, if I connect my vector with my x-axis, I have formed a right triangle. All right, since we are converting from polar to rectangular, and rectangular coordinates use two numbers, written as an ordered pair. One is an R and one is a U. we are going to label the sides of my right triangle R and U, okay? R is the x value. You can remember this as x goes right and left, R, right and left. And the U is the one that goes up and down, which is your y. Okay, so we have R and U. All right, so from my polar coordinate, we've drawn the diagram, we've labeled our triangle. Step 2, we're going to find the opposite side's length. And we are going to use this using our trig function. All right, anytime we're finding the opposite side, we're going to use the function sine. All right, so let's look at finding our opposite sides. Opposite of 57 is u, and we know we're going to use this sine function. So sine of 57, and sine is opposite over hypotenuse. So it's the opposite, which is u, over the hypotenuse, which is our vector, 4. All right, so in order to find u, we're going to multiply sine of 57 times 4. If we plug that into our calculator, u is going to be equal to 3.35. Okay, so we have found our opposite side. Step 3 is to find the adjacent side length. All right, and if we're finding the adjacent side, we're going to use the cosine function. All right, so we're finding the adjacent to 57, so we're going to use the cosine function. So cosine of 57 is the adjacent, which is side R, over the hypotenuse, which is our vector of 4. So in order to find R, we're going to multiply 4 times the cosine of 57. When we plug that into our calculator, we get 2.16. All right, so we have found R, we have found U. The last step is to write the rectangular coordinate. Okay, remember rectangular coordinates are written as ordered pairs. So we're going to write it as an ordered pair. Remember, in our ordered pair, normally x would come first, y would follow. In this case, r is going to come first, u will follow. Okay, it's in alphabetical order. So our r value is 2.6. Now notice r from the origin is on the positive axis. So 2.16 is positive. So we have 2.16, and we're going to label it r. U is 3.35. Now notice 3.35 is also on my positive axis, so it's going to be plus 3.35, and we're going to label it U. And that is how we would write a rectangular coordinate. Okay? All right, let's work another example together. All right, example 2. We are going to convert 7 with an angle of 230 degrees to a rectangular coordinate. All right, so we'll follow our steps. The first step we want to do is draw a diagram and label the right triangle. This is often the hardest part of the whole thing. All right, so we know that we're going to have a coordinate plane. We want to start with our angle first. Okay, always start with the angle. I have a 230-degree angle. It starts from the positive x, and I'm going to go to 230. Now from this axis to this axis is 90. If I keep going, it's 180. Now if I went all the way to this next axis, it would be 270. So since 230 is somewhere between 280 and 270, I'm going to go somewhere in between these two axes. You don't have to get the measurement exactly right, just estimate it about where it is. Okay, then our vector length. The vector always starts from the center and goes out to meet the angle, and our vector has a length of 7. Okay, so our angle is 230 with a length of 7. Now, we're going to complete a right triangle by connecting the end of my vector to my x-axis, which means that this right here is our right triangle. So when we're dealing with this angle here, we're only dealing from this point here to this point here. Okay, we're not going to call it the 230-degree angle. We're only dealing from here to here. So if from my positive x to this point here was 180, I want to go from 180 to 230. So I'm going to subtract 230 minus 180, and that will mean that my angle then is 50 degrees. Okay, we're looking for the angle inside the triangle. So I have a 50-degree angle. Okay. All right, then we need to finish labeling our right triangle. The x-axis is R, for right to left, and the one up and down is U. Okay, so we've labeled it, we've drawn it out. The next step is to find the opposite side length using the sine function. So we're going to find the opposite of this 50-degree angle using sine. So the sine of 50 is the opposite, which is U, over the hypotenuse, which is 7. We multiply 7 times the sine of 50, and that will give us 5.32 for our U value. The next step is to find the adjacent side length using the cosine function. So we're going to do the cosine of that 50-degree angle, and we're going to find the adjacent side. Well, the adjacent side is R. R is the adjacent side, and so that's going to go over 7. So in order to find R, we multiply 7 times the cosine of 50, and that will give me 4.48. And finally, the last step is to write the rectangular coordinate. Now notice this time, we're still going to write them alphabetical order, R and then U. Notice that the R value is on a negative axis, so my R value is going to be negative. So it's negative 4.48, we label it R. And then U is also on a negative axis since it's going down. So it's going to be negative 5.32 U. All right. This next example, I would like for you to try on your own tonight. We have a segment, a vector of 42 with an angle of 340 degrees. So go ahead and try that example on your own, and we will check it tomorrow. We're going to move on to similar triangles. We just have one example that I'm going to walk through very quickly with you. These are two similar triangles. We have their side lengths represented by variables. Normally we've been doing this with numbers, but we're going to do it with variables. We're going to solve for one variable in terms of the other. So in this case, I want to solve for side D. So we're going to look for D. The way we're going to do this is write equal ratios. And then we're going to go ahead and cross multiply and divide. Okay, so first we need to figure out what sides are similar. Now notice, this angle here and this angle here are the same. They're equal, which means their sides are going to be, they're going to be similar sides because we have equal angles. So side C is going to be equal, or going to be a ratio of D. So we have C is to D. Now also notice that because we have vertical angles here, they are equal, which means these other angles that are left over are going to be equal as well. So then, since this angle is across from A, this angle is across from B, A is to B. Now we're solving, in this case, for D. So in order to solve for D, we're going to multiply C times B and divide by A, and that's going to be equal to D. So this is solving similar triangles in terms of variables instead of how we have been doing it with numbers.